to you today about using astronomical spectroscopy to probe the physics and chemistry of gas, stars, what have you, in the universe. And I'm Nissim. Please don't call me sir. Please call me Nissim. And what else? I tend to speak really fast. I should give you the usual caveat at the start of the talk that I try to remember to slow myself down at the start of every talk, and I usually forget in the space of about 3 or 4 minutes. So I will rely on you to kind of wave a hand, do something in Zoom and attract my attention in case I'm going too fast. And of course, please feel free to ask questions or whatever in the middle. It's absolutely fine to not hold questions for the end. Right. So I'm going to be telling you about astronomical spectroscopy, and there will be, of course, a focus on the radio spectroscopy. I will try not to be too nasty to optical folk, but I will be slightly nasty to optical folk. And of course, the telescope the background to that first slide is a giant meter wave radio telescope, the telescope that we know and love here in NCRA. And the person who designed it, who led the designing team and who led the building team and who led the using team, Govind Swarup, unfortunately, sadly passed away about a few months ago. And the reason the GMRT was built, the primary reason that the GMRT was built, was planned about 30 years ago, 35 years ago, was to do spectroscopy in the 21 centimeter line. And I will talk about this in my second talk on Monday. But for now, I'll just leave you with a taster that the primary science goal of the GMRT was essentially 21 centimeter spectroscopy. So moving on, this is the broad outline of the talk. I'll give you a little bit of a feeling on what are spectral lines and why we care so much about them. I'm going to spend a fair amount of time talking about various types of astronomical spectral lines. And this talk, as you will see, will have a strong cosmological bias, partly because the range of topics that you can cover in spectroscopy is almost unimaginable. The physics is vast. The kind of stuff that you can do is vast. So I will just leave stuff open as a bunch of, these are the bunch of tools that we use to probe conditions in the universe. I will try to tell you why you should love radio spectroscopy. Of course, obviously one should love radio spectroscopy as opposed to all other types of spectroscopy. But this should be obvious to all of us. But I will give you a few reasons why you should do this in case in case you lose the faith, so to speak. And finally, I'll tell you a little bit about a few good radio lines and what you can do with them. And I will emphasize a strong cosmological bias over here. And I'm going to then leave things open. I will not spend too much of time on detail. So if you have any questions, just feel free to jump in or ask them at the end of the talk. So what are spectral lines and why do we care so much about them? So spectral lines are basically quantum mechanical transitions in atoms or molecules at some specific frequency. And these happen because the atom or molecule has two possible energy levels, two in the simplest case, and it makes a transition from one level to the other. If it makes a transition from the upper energy level to the lower energy level, the line is in emission. If it makes a transition, if you like this is associated with the emission of a photon, and the line is in emission. On the other hand, there's a background source, and the atom or molecule absorbs radiation from the background source, causing the atom molecule to transition from the lower level to the upper level. The line could be an absorption. And these lines are narrow. By narrow, I mean, these are not broadband phenomena. These are lines which are typically of the order of, they give you information about the spread of the line is inherently narrow. The spread is governed by quantum mechanics. And then over and above that, because you have lots of gas, you have lots of these atoms and molecules, some of which are moving towards you, some of which are moving away from you, you wind up with a slight width. But this width is tiny on the scale of spectra. So you need high spectral resolution to be able to identify these lines. As I said, these lines may be an emission or they may be an absorption. And the reason, usually you see them in emission when you have a large mass, when you have a lot of gas towards you. And you see them in absorption when you have a high, what is called a column density, a lot of particles towards a background star or quasar. And then you have absorption of the light of the star or quasar. I'll show you an example of both emission and absorption spectra shortly. The physics is vast. So for example, the simplest transitions that we know of are electronic transitions, and I'll show you examples of those in a short while, where you simply have a jump that happens from one principal quantum number level to another principal quantum number level. So if you think of the Bohr atom in hydrogen, it's from n equal to 2 to n equal to 1, n equal to 3 to n equal to 1, etc., etc. And those are the simplest transitions. Then there's fine structure, there's hyperfine structure, there's molecular rotation, there's inversion, there's lambda doubling, there's L-type doubling. There are all kinds of transitions that you could have, and you have mixed transitions where you have mixes of these different physical effects. And the idea is simple. The idea is that any physical effect that can change the energy of an energy level will essentially give you two energy levels. You can always have a transition between these levels. Of course, some transitions may be forbidden or semi-forbidden, but anything that gives you a separation in energy provides the possibility of a transition from one level to the other, and hence the possibility of a spectral line. And this is interesting because it kind of tells you that you can use these spectral lines, ouch, I beg your pardon. You can use these spectral lines to probe both the physics and the chemistry of the emitting or absorbing region. And this is kind of obvious because you could imagine that, if you take a gas, for example, in equilibrium, then the relative strengths of different lines will tell you a lot about the conditions, depending on the nature of the equilibrium, if it's thermodynamic equilibrium, pressure equilibrium, and so on. The important thing, though, is that the line frequency essentially identifies the line. I say that with a caveat that works in regions where there are, in frequency parts of the band, where there are not too many lines. So for example, in the optical or the ultraviolet part of the band, the line frequency essentially identifies the line. So you measure the line frequency in the lab, and you simply go out and take a spectrum of a quasar or a star or a galaxy or anything at all. And if you see a set of lines in there, if you see one line, of course, as you'll see in a second, you don't know what line that is. And that is because if that object is moving, then you will wind up with a shift in the observed frequency of the line because of the motion of the object. And this is basically just a Doppler effect. But if I see two lines from that object, then both lines will be shifted by the same amount because of the Doppler effect. And so therefore the ratio of the line frequencies or the line wavelengths will be exactly the same as in the lab. And so this can be used very easily to identify the lines. And this can immediately, you can see, also be used to identify the motion of the object. Because I can now measure, just by identifying the lines and then looking at their measured frequency, I can tell you how fast the object is moving away from us or towards us. And this is great. In fact, this was used to measure the expansion of the universe about 100 years ago, 90 years ago. And you can basically determine the object's kinematics from the redshifts or blue shifts of its spectral lines. And this is foundational in astronomy. So let's go back a second and take a look at what I'm talking about over here. So this is a star going around in an orbit. The top right figure is a star going around an orbit. And you see these black absorption lines from gas in the outer layers of the star. And you can see when the star is moving towards us, these black lines move towards the bluer part of the spectrum. And on the other hand, the star is moving away from us as it's doing now. The black lines move towards the redder part of the spectrum. That's basically blue shift and red shift. But all the lines move in unison. All the lines move in the same direction at the same time. And that immediately tells you that it tells you you can identify these lines easily. The line ratio, the ratios of the wavelengths will stay constant. But the second thing is that you can immediately work out if the object is moving away or towards you. The lower figure shows you an example of a beautiful galaxy, a disk galaxy, M33, imaged in the H1 21 centimeter line. And what's been done over here is that the H1 line, the image, has been color coded by the velocity of the gas. And so what you see is that the lower the left side of the galaxy is color coded in red. The right side of the galaxy is color coded in blue. And what this means is that the part of the gas in the galaxy on the left side is moving away from us. The gas in the galaxy on the right side is moving towards us. And you can see that all the gas on the right side is moving towards us. All the gas on the left side is moving away from us. And what is happening is that the galaxy is in rotation. And this is a beautiful way of measuring the large-scale kinematics of an object. So where now the emitting regions are extremely huge. It's a gigantic galaxy, but you can actually see the entire motion of the galaxy by the motion of the individual parts. You can actually see coherent motion of a gigantic object. And this, for example, is used, you'll see on Monday, to determine rotation curves of galaxies, to essentially measure the speed of the galaxy as a function of the radius of the distance from the center of the galaxy, and thence to determine the mass of the galaxy, the total mass, and thence to conclude or to determine that there must exist dark matter in the universe, much more than the baryonic matter that you observe. And so you can see that the implications of such measurements of kinematics can be extremely deep. Uh, just a simple measurement, the fact that you have Doppler motions when an object is moving towards you or away from you, can be used to obtain detailed, deep information about the physics of the universe. And that's the game basically in spectroscopy. And that's, if I had to pick one thing that makes spectroscopy special, I would say it's the determination of physical kinematics. It's very hard to do this from from continuum, from broadband observations. Spectroscopy allows you to get kinematics. And of course, you can do a bunch of other things. You can do, as I said, you can do relative strengths of different lines. You can do the strengths of lines of different species. You can do excitation. All that is physics and chemistry. But kinematics is special because it's very hard. We can't go off, pop off, take a walk and measure and sit on top of a quasar and see how fast it's moving. But the kinematics of an object can give you the third dimension of information about astronomical objects, and which you can't get by any other means. And so I'd like you to take that home. Kinematics are fundamental in astronomy, and spectroscopy gives you kinematics. So let's talk about a bunch of spectral lines. And perhaps unsurprisingly, given that atomic hydrogen, neutral atomic hydrogen, which is demarcated as H1 or HI, if you like, H1 Roman, H1 is the most abundant element in the universe. In fact, hydrogen, atomic and neutral and ionized, is the most abundant element. It's about 75% of the mass in the universe. And atomic hydrogen in galaxies is the most abundant species in a galaxy. And this kind of immediately tells you that the spectral lines of atomic hydrogen are probably the most important lines that you have in astronomy. And the basic lines are, for example, Lyman alpha, or Lyman beta, Lyman gamma, which basically are electronic lines where you have transitions from to a ground principal quantum number of 1, the ground state, and transitions from 2, 3, 4, 5, n equal to 2, 3, 4, 5, and so on. And Lyman alpha is at about 1215.71 angstroms. So these are deep in the ultraviolet. And you have a series of lines, which is called the Lyman series. You also have a corresponding series called the Balmer series, which is actually what Bohr used to work out the semi-classical model of quantum mechanics. And those are called Balmer alpha, Balmer beta, and so on. In astronomy, they're often called H alpha, H beta, H gamma, and so on. And these are again electronic lines, and that shows you the figure on the bottom left shows you an example of these electronic transitions for a hydrogenic atom, which has an atomic number of Z. And they basically, you have jumps that happen from, say, for example, n equal to 3 to n equal to 2, and which comes with the emission of a photon. In hydrogen, these give rise to what are called the Lyman-Balmer, Paschen, bracket fund, and so on series. For Balmer alpha, the line is at 6,562.8 angstroms, well in the optical, which is the reason that you actually see these lines fairly easily, both in the lab and in astronomical circumstances for nearby galaxies. For Lyman alpha, you have to actually put a spectrograph in space. So you need to do observations with something like the Hubble Space Telescope or the AstroSat instrument. And so these are examples of the simplest kind of transitions, which are transitions between principal quantum number energy levels. And they're the ones that we know and love. Most of you would probably have studied them at probably the second year, I would think. I don't think we had that 25 years ago, but I guess the students are much more advanced right now. But these are, as I said, the ultraviolet and the optical. A line which is perhaps, I will argue this on Monday, the most important line in astronomy is also arises in atomic hydrogen. And this is called the H1 21 centimeter line. And this is very different in its physics. This is a hyperfine transition. So a hyperfine transition arises because if you take atomic hydrogen, atomic hydrogen is made up of an electron and a proton. And each of these can have spins. And each of them can have a spin which is either up or down. And therefore, you have two possible orientations of the electron spin relative to the proton spin. The state in which the electron spin and the proton spin are parallel has a slightly higher energy. This is called hyperfine structure, from the state in which the electron and proton spins are anti-parallel. And so therefore you can make a transition from the upper state to the lower state. And this is within the ground principal quantum number state of hydrogen. It's within the ground state. And you can make a transition from this upper hyperfine state to the lower hyperfine state. And that produces a photon at a frequency of 1420.40575 megahertz, which corresponds to a wavelength of about 21 centimeters. And so therefore, this has been immortalized as the H1 21 centimeter line. And this will be the focus of my talk on Monday. This gives you a humongous amount of information about the physics of gas in the universe. And so that's an important line. And as you can see, it's very different in terms of the physics from the Lyman and Balmer and Paschen series that we see in the UV and the optical and the near infrared. In addition to that, you have things called radio recombination lines, which are actually like the Lyman, Balmer, Paschen, and so on series, except that these are very high N. So the transitions are happening between, they're also electronic transitions, but they're happening for N equal to, for example, 100 to 99. And that causes the line to shift into the radio. And this gives you information, for example, about the density and temperature of ionized gas frequently, or of the warm neutral medium. You also see such radio recombination lines in helium and carbon as well, especially at the lower frequencies in the radio, such as frequencies covered by the GMRT. And so hydrogen is perhaps the most important element in the universe, and hence the lines of hydrogen are the ones that we see most easily, typically. What about other atomic species? So, in this kind of somewhat parochial way in astronomy.
Namaskar, Vijay.
I beg your pardon?
हाँ, मैं रूम पे आप आ सकते हैं.
Sykes, you might want to mute yourself. So, in astronomy, 75% of the gas of the universe is hydrogen, 25% is helium, and everything else is referred to as metals. So everything with an atomic number higher than 2 is called a metal. It is kind of a funny thing for normal humans like us, where we're used to things like iron and so on being called metals. But every single species with an atomic number of 3 or larger is called a metal in astronomy. And atomic species, for example, iron, magnesium, silicon, carbon, oxygen, chromium, zinc, all of these species, sulfur, produce absorption or emission at the ultraviolet or optical wavelengths. And this plot at the bottom over here shows you an average quasar spectrum, where what Wilkes and company did was that they basically just averaged over 1,000 quasars in the Large Bright Quasar Survey, just to take a look at what the average quasar spectrum is like. And so this is a plot going from about 1,000 angstroms over here on the left to about 6,000 angstroms on the right. And what you see is very strong Lyman alpha emission, 1215.7 angstroms. Then you see this funny thing called C4. In astronomy, just to complicate matters, remember I said that H1 or H1 is neutral atomic hydrogen. Similarly, C1 is neutral atomic carbon. C2 is singly ionized carbon. C3 is doubly ionized carbon, and C4 is triply ionized carbon. And the bulk of carbon in the universe is usually certainly in the digalactic medium, is in either the singly ionized state or the triply ionized state. In galaxies, in a singly ionized state, the temperatures are high. And you see a very powerful line in galaxy and quasar spectra at about 1,550 angstroms. It's actually a doublet. At this resolution, you don't really see it as a doublet, but you see a single very powerful line. There's a semi-forbidden line from doubly ionized carbon at about 1,900 angstroms, which is again seen only, or see very strong quasar spectra. There's a very strong magnesium 2 or singly ionized magnesium doublet at 2796 and 2803 angstroms over here. And then you have the Balmer series, where you have H beta at 4861 angstroms, kind of a bump that you barely see over here. H gamma at 4340 angstroms, and H delta really faint over here. Then you see an oxygen triplet, which comes from doubly ionized oxygen, and which has 3 lines over here. There's also a singly ionized oxygen doublet, which is sitting somewhere over here at 3727 angstroms, which are not marked over here. And if you go beyond, further beyond this, to about 6,600 angstroms, you see a very powerful H alpha line, Balmer alpha, the first line of the Balmer series, of which you see three elements over here. You also see a line over here at the extreme left of the spectrum, which is O6, quintuply ionized oxygen, which is also a doublet at about 1035 angstrom. This turns out to be a very interesting line to probe conditions in the halos of galaxies, in the hot halos of galaxies. So this is a set of standard lines that you see in quasar spectra. If you, of course, tune your spectrograph to cover these lines at the redshift of the quasar. So you have very strong hydrogen lines, and you have strong metal emission lines. If you observe a galaxy, you see some subset of these lines. And the important thing is that the ratio of the line strengths will be different for different types of galaxies. So the line strengths will tell you a lot about the kind of galaxy that you're observing. So that's an example of an emission spectrum in the optical, or the ultraviolet and optical. What happens, suppose you have, if you put this quasar at a very high redshift, or some redshift, and you take a spectrum of that quasar. Now what happens is that you have the whole intergalactic medium between you and the quasar. In addition to that, there could be galaxies between you and the quasar. And then things get interesting. This is not, now you will not see simply an emission spectrum of the quasar. You superimposed upon the emission spectrum, you have absorption spectra. And that's shown over here, where what's been plotted over here is the spectrum from a background quasar at a redshift of about 3. And I'll tell you how we know that in a second. And the sightline to the Earth is over here. And of course, there's gas between us in the intergalactic medium. There is gas. I'll tell you how we know there's gas in a minute. But let's assume for now that there is gas. And let's say there's a galaxy sitting somewhere over here. So this thing that you see over here, which is marked a dashed line in the red, and then the solid line in the red again, that's the quasar spectrum. And so this is the same Lyman alpha emission that we saw a little while ago. It's very, very, very strong. That's blended with a line from quadruply ionized nitrogen. And then there's a silicon 4 line, a weak silicon 4 line, which you didn't see in the earlier thing, which was quite weak. And then the same carbon 4 line that we saw a little while ago. And those are the emission lines. And here, as you can see, you're plotting observed wavelength. And so you'll say, hang on a minute, the Lyman alpha line is at 1215 angstroms. How did it come to nearly 4,900 angstroms? Of course, the reason it moved to 4,900 angstroms is that you're plotting observed wavelength, and this corresponds to a redshift of 3. So the line is shifted by a factor of 1 plus z, which in this case is a factor of 4. And so you need to multiply 1215.71 angstroms by roughly 4. And this tells you that this quasar is at a redshift of about 3. And all these lines now, the SI4 line, for example, which is at 1550 angstrom, the rest frame, is now at about 6,200 angstroms, and so on with silicon. And that's the reason that you don't see the optical lines, the rest frame optical lines. They've all been shifted by a factor of 1 plus z up, and so now they're lying in the near infrared. But what are all these weird absorption lines that you see over here? What's this weird, this mess that you see, which is blueward of the Lyman alpha emission line? What these are is essentially Lyman alpha absorption from atomic hydrogen lying between us and the quasar. So this is atomic hydrogen sitting in the intergalactic medium. And this is called the Lyman alpha forest. And because hydrogen has such strong lines, and there's so much of hydrogen in the universe, even tiny amounts of hydrogen can produce absorption. So at every redshift over here between us and the quasar, a little bit of hydrogen will produce absorption at that redshift. So for example, at let's say 4,000 angstroms, this corresponds to a redshift which is 4,000 divided by 1215 minus 1. So roughly a redshift of about 2.2, 2.3 or so. And so from the wavelength of the line, you immediately know the redshift of the gas that's producing the absorption. And you might say, hang on a minute, how do I know that this line is actually Lyman alpha? Why can't it be something else? And the answer is you don't know actually. All you know is that the bulk of this absorption is coming from Lyman alpha. There could be other metal lines from gas at other redshifts in between, which also contributes some absorption. But the bulk of the absorption is Lyman alpha. And then every so often, superposed upon this forest, which is this thicket, this cluster of very fine absorption lines, you see this extremely powerful, broad absorption line. And this arises because of what is called damped Lyman alpha absorption. When you have a lot of hydrogen, of neutral hydrogen towards a quasar, it turns out that you actually see a quantum mechanical effect which happens because of the uncertainty principle. So you have what is called natural broadening of the line levels. A way to think about this physically is that uh, a single energy level cannot have a single energy, or one energy level cannot have a single formal well-defined energy with delta E, the error on the energy being zero. This is just forbidden by the uncertainty principle. Uncertainty tells you that every energy level, except for the ground, if you like, has to have a spread in energies. Otherwise, that level will decay to a lower state on a time scale given by delta E delta T greater than or equal to H cross. And so this implies that every spectral line has a natural width associated with it, which is driven by the width of the energy level, the energy width of the energy level. You can make transitions to slightly different energies for a single spectral line. And normally, of course, this is a quantum mechanical effect. You don't really see this in real life. You see this in real life only for Lyman alpha because that's a super strong line and because there's so much of hydrogen in the universe. And so what you actually see is these Lorentzian wings, which go to infinity like 1 upon lambda square plus a square, where a is a quantum mechanical constant. And they kind of go slowly to infinity. And you can actually measure the shape of these wings and demonstrate that the line shape is actually Lorentzian. It actually has its functional form 1 upon lambda square plus a square. And from that, you can immediately know that the column density, the number of particles, the number of neutral hydrogen atoms along your sight line must be very large. And from this, you can conclude that this object must be a big galaxy because such high column densities, such high amounts of hydrogen are not found in the intergalactic medium. They're found in the local universe only in galaxies. So this has been used for about 35 years, since about the mid 1980s, as a signpost for the presence of a galaxy towards a background quasar. So these are called damped Lyman alpha absorption lines. And this is used as a signpost that there is a galaxy over there. And having found this galaxy, having identified this galaxy, now you can go and look at it and in the optical or in the radio or whatever, and try to understand what kind of a galaxy it is. What you also see, and this is interesting, is the redwood of the Lyman alpha line. So you have the Lyman alpha line that are about 4,800 angstroms. And blue out of this, you have all this horrible Lyman alpha forest. And it's very hard to see metal absorption in this because there's so much of hydrogen absorption. But redwood of the Lyman alpha line, the spectrum is quite clean. And the reason it's clean, of course, is that if there's hydrogen at a redshift higher than the quasar, that's behind the quasar. So it won't produce absorption. So therefore, you won't see hydrogen absorption over here. You'll only see it bluebird of the quasar. But what you do see over here is these narrow absorption lines. And these lines arise from metals in this galaxy, usually, and sometimes from the forest. So you'll see nickel absorption, for example, over here, silicon absorption over here. This should be carbon 4, not Ci4. Ion absorption line over here, aluminium absorption, neutral magnesium absorption, nickel absorption, silicon again, aluminium 3. And the relative strengths of these lines tell you about the metal abundances in this gas in the absorbing system, and they can be used again to probe conditions in the absorber. So these damped Lyman alpha absorbers are extremely interesting in terms of understanding physics and chemistry of high redshift galaxies. And they've been used for this for about 30 years. But that's an example of what you can do in the optical or the ultraviolet. All these lines are rest frame ultraviolet, and they're only redshifted into the optical. And so this kind of gives you, although I said I would bash the optical folk, clearly, the optical waveband is extremely rich in spectral lines. And let me emphasize, it's extremely rich in atomic spectral lines. There are molecular lines. Molecular hydrogen, for example, produces the Lyman and Werner bands at about 1100 angstroms and slightly below. And these are usually, for an absorber like this one, these will be in the Lyman alpha forest, and they can be detected. But there are not too many other molecular lines that you see. You do see HD, deuterated hydrogen, which also produces absorption in the ultraviolet. You see some weak carbon monoxide lines. But the bulk of the lines in the ultraviolet and optical actually are coming from atomic transitions. So let's make a shift now from the optical and the UV. Let's move to the infrared. So the bulk of the lines in the mid-infrared, which is something like, let's say, a couple of microns to about 20, 30 microns, the bulk of these lines come from fairly strange species. These species are called polycyclic aromatic hydrocarbons, and they're basically, complicated molecules, usually planar molecules, which are made up of interlocked benzene rings. So things like anthracene, the fullerenes are example of PHs, and you have extremely complicated molecules that have been detected in the interstellar medium in molecular clouds. And these molecules have these carbon-carbon bonds and carbon-hydrogen bonds, and of course, a large number of these bonds. And you wind up with the possibility of these bonds bending, stretching, and vibrating. And all of these give you different energy levels, and you have very strong emission coming from these PHs, polycyclic aromatic hydrocarbons, at the mid-infrared wavelengths. And these are powerful lines, not so much because there are lots of PHs. The mass in PHs in a galaxy is quite small. It's about a factor of 50 to 100 less than that of, say, atomic hydrogen. But these lines are strong lines. But more importantly, every single pH molecule which has a CH bond, for example, will produce this CH bending mode. It'll produce a CC stretching mode. So all these molecules will produce emission at approximately the same frequency. So these give you fairly wide lines because depending on the exact molecule, you get a slightly different frequency. And the effect of this is what you see in the figure at the bottom, where you see this morass of lines sitting between something like about 3 micron roughly and about 20 microns. All of these lines are pH lines, or most of these lines are pH lines. And they come mainly from these bending, stretching, vibrational modes. I beg your pardon. And you can see, so this is an example of a spectrum of a galaxy where this is 1 micron. So the optical is over here. The UV is even further. This is the near infrared. And then this is the mid infrared. And you can see that these lines for a typical galaxy are quite bright. Even for the Milky Way, they're quite bright. But if you take a big galaxy like a starburst galaxy, they are extremely bright. They can be detected fairly nicely. But the problem, as you'll see in a minute, is that these lines, because they're in the mid-infrared and our atmosphere is not transparent in the mid-infrared, it's very hard to see these lines with telescopes from the ground. You have to go to space to see them, or on a flight. In fact, the original observation of these lines were done with the Kuiper Airborne Observatory, which is basically a telescope in a plane that used to fly around the place and take observations at a sufficiently high height so that you were above the mid-IR layer, if you like, the layer that blocks the mid-IR. And the Spitzer satellite, which is still operational, operated for about 17, 18 years, still in its kind of slow, warm mode right now. And that carried out detailed observations of pH features in both the Milky Way and nearby and high redshift galaxies. In fact, one of the primary science motivations of Spitzer was to study pH features in galaxies. And the reason pHs are so important is that they have these really weak, weakly bound electrons, and a lot of them. And these electrons can actually be very easily ejected photoelectrically from the pHs, carrying kinetic energy. And they actually are the primary contributor to heating the interstellar medium. So if you want to understand the physics of the interstellar medium, you must understand pHs. And people have appreciated the importance of pHs probably from around the 90s onwards. And now they are considered to be a foundationally important part of the interstellar medium of galaxies. So moving on, as you go to slightly longer wavelengths into the far infrared, so say something like 50 to about a few hundred microns, there you have what are called, you have mainly fine structure transitions in metals. And the most important of these lines is what is called the C2 or C plus ionized carbon 158 micron line, which is sitting as you see over here. And this curve over here that you see is actually the emission from dust, from heated dust in the galaxy. And the C plus line is sitting at about the peak of the heated dust of any galaxy. In addition to that, you have, for example, the oxygen 163 micron line, which is sitting over here, slightly weaker than the C plus line. The oxygen 388 micron line, which is sitting over here. There's a nitrogen, singly ionized nitrogen 122 micron line over here, which is somewhat weak. There's a nitrogen line at 205 microns over here. So these are all fine structure lines. And these lines, as you, again, have a problem because they are sitting in the far infrared, which you can't observe from the ground. Again, you need to send satellites into space to observe these lines. So, for example, the Herschel satellite, one of its primary science goals was to observe these far infrared spectral lines from galaxies and the nearby universe. But one beautiful thing of the expanding universe is that for high redshift galaxies, galaxies say a redshift of larger than 1, these 158, for example, the C plus 150 micron line gets redshifted into the to longer wavelengths, and essentially it enters the radio band. So it's easier to observe, funnily enough, it's easier to observe high redshift galaxies with telescopes on the ground in these lines than it is to observe nearby galaxies. Because to observe nearby galaxies, I have to build a satellite that goes to space and put a telescope on it. While to observe a high redshift galaxy, I just need to build a telescope on the ground that can observe, let's say, over here in this part of the band. And as you'll see in a bit, the the ALMA observatory is exactly built for this to go to about a frequency of 1 terahertz or about, if you like, zero point 0.3, somewhere about here, zero point 0.3 millimeters. In addition to the far infrared spectral lines, as you go further into the towards the radio to longer wavelengths, you wind up with strong molecular lines. And these are rotational lines. The bulk of the strongest of the molecular lines are molecular rotational lines. The most important of these lines are the carbon monoxide molecule. So, most of us don't much care for carbon monoxide on the planet, given that, it's a very nasty species. But CO is really special in the interstellar medium because CO is the second most abundant molecule in the interstellar medium. The most abundant molecule, of course, is molecular hydrogen, but molecular hydrogen is very hard to detect directly in its emission. We can talk about that later if you like. CO is relatively easy to detect in emission. And so CO has been used to trace the mass of molecular hydrogen in galaxies for about 30 years or so now, 35 years now. And CO is an interesting species. It's got this set of molecular rotational lines starting at 115.27 gigahertz and then going up by approximately integer units, so 115.27, 230.5, 345, 460, and so on gigahertz. And they go to from higher and higher rotational levels. And you see this complex of lines if you can actually go and observe each line from a galaxy. And that's nice. It gives you information about conditions. In addition to CO, you also have very strong lines from water. So, and water is a more complicated molecule than CO. So water has very strong rotational lines. So for example, this powerful line that you see over here, this really powerful line, is the ground state water line at 556 gigahertz. And this line over here at about 787 gigahertz is also a water line. But this is the most powerful water line there is. And in some galaxies, the ground state water line is comparable in its strength to the CO ground state lines or the CO, say 3 to 2 lines. And that is again an important probe of conditions in a galaxy. In addition to all of these nice rotational lines, which are relatively simple physics, you also have a slew of molecules in the interstellar medium. As of today, more than 100 molecular species have been identified in the Milky Way and nearby galaxies, and these include extremely complicated species. So you have ketones, aldehydes, alcohols, all kinds of stuff in the interstellar medium. And people are now trying to actually find amino acids. The simplest amino acid, glycine, is the subject of many searches now, with the primary aim being to actually find the building blocks of proteins and of life in the universe. So glycine is the simplest of these amino acids, and people are trying very hard with telescopes like ALMA to look for glycine. And these lines, the spectral lines from these species, these molecules, one, they come from very complex physics, but that is interesting because it gives you a lot of information about conditions. And they come roughly in the frequency range of 1 to 1,000 gigahertz. So somewhere about, starting from about over here, and then going out, starting from somewhere about here and going out to, this is about, there's 1 millimeter, and 1 millimeter corresponds to about 300 gigahertz. So they go all the way out to about 1 gigahertz. OH lines, for example, at 1.6 gigahertz. And this part of the spectrum is extremely rich at the level where you often have multiple lines from at a single frequency from different species. And so this has resulted in immense embarrassment where, for example, somebody observes a line and jumps up and down saying, hey, I found this wonderful line. And then somebody else comes along and says, I have bad news for you. There's a much simpler molecule which has a line at exactly the same frequency. And what you've actually seen is not this very, very complicated molecule that you thought you saw, but this much more simple molecule. The reason this happens is that molecules are complicated. So they have very complicated energy levels. And very often it's hard to measure all these different energy levels in the lab. I have actually been nearly embarrassed by this myself, that we were doing a search of molecular oxygen at a redshift of zero point 0.9, and which has never been seen before in redshifted systems and has barely been seen in the nearby universe. And we thought we had a detection of molecular oxygen with ALMA, sorry, with the VLA. And then we realized that it was possible that the line that we were seeing was actually an absorption from acetaldehyde. And we weren't sure. So we decided to not publish. And we instead went to ALMA and tried to observe another oxygen line, molecular oxygen line, which should have been detected if this were oxygen. And it turned out that we did not detect the oxygen line, but we did detect another acetaldehyde line confirming that this was acetaldehyde. And so this is the kind of thing that you have to worry about. In fact, there have been people who have actually published claimed detections of glycine, which turned out to not be real. Very recently, some of you would have noticed this claimed detection of phosphine in the atmosphere of Venus. That's an example of a line where we are not sure if that line comes from phosphine or from some other molecule. And you need to really go and look for other species, for other lines from the same molecule to confirm that the absorption or emission that you're seeing is really from the molecule that you think it's coming from. So this part of the band is complicated. It's complicated because of the density of lines. Oh, another way of quantifying this is that a survey was done of this very famous molecular cloud region near the galactic center of the Milky Way, what is called Sagittarius B2. And about 20% of the lines that were detected in this complex, from a frequency range of about 90 gigahertz to 110 gigahertz, 20% of the lines have not been identified in the lab. You don't know which lines these are. All you know is that you see the lines in astronomical circumstances. You have no damn clue what these lines are. And that tells you how dense and how complicated this part of the band is. But it also tells you how interesting it is in the sense that it gives you access to extremely interesting physics, most of which you will not be able to see in the lab. The only reason you can see this physics or chemistry is that there's so much of this kind of gas in the universe. It's very hard to produce this kind of gas in the lab and these conditions that excite these lines in the lab. Okay, so why should you like the radio so much? The first reason that you should like the radio, of course, has to do with the fact that we live on the Earth. And the Earth has this nasty thing called the atmosphere, which maybe I shouldn't call it nasty, because if it didn't exist, then we'd all be dying of cancer. We wouldn't be around right now. We wouldn't have had evolution to produce humans. But what the atmosphere does is that it blocks a lot of the radiation coming to us from external objects. So this is a plot over here of the atmospheric opacity. So the top graph, shows you that the atmospheric opacity plotted as a function of wavelength, starting from the gamma rays, going all the way out to the radio. And this is in log units, of course, in wavelength. And so you see that the atmospheric opacity is 100% in gamma rays, X-rays, ultraviolet. And this is good because it's this radiation that could really do us severe harm. Then you see a spectacular dip in the atmospheric opacity. It goes to nearly zero. And this, of course, is the visible band. And that's why they're shown as blue, green, whatever, yellow, and red. And that's this very tiny region of the spectrum called the optical. Then as you go, then the atmospheric opacity tends to rise slightly in the near infrared. And then you have these jagged regions in the near to early mid infrared. There's a small hole at about 10 microns where you can observe where it drops to about maybe 20, 30%. And then in the mid to far infrared, again, the opacity is almost 100%. All the way out to about a millimeter. And then as you go to longer wavelengths, the opacity tends to drop. In this part of the band, the opacity is coming mainly from water and oxygen in the atmosphere. And so if you go to high altitudes, you can actually overcome some of this. So for example, ALMA, which is at the Atacama Large Millimeter Array, is at an altitude of about 5,000 meters, 5,040 meters in the Atacama Desert, where it's really high and dry. And as a result of which, you can actually observe with ALMA all the way down to about zero point 0.3 millimeters over here. So well in the region where it looks like it's 100%. There are parts of the band where you can actually observe with ALMA. But if you were, for example, the GMRT side, it would be very hard to observe at wavelengths above about, say, a centimeter or so. And then you have this wide frequency range going from about a centimeter to about nearly 20 meters. And this is the radio band. And so you can see, and over here, the atmospheric opacity is basically zero. And this is a humongous frequency range. You can see this is about 2.5 to 3 orders of magnitude in wavelength. The optical, which is the basis of historical astronomy, is a tiny little wavelength range. It goes from about 3,000, 3,500 angstroms to about 7,000, 7,500 angstroms, right? So it's a factor of 2. This is a factor of nearly 1,000. And that makes the radio special. You can actually do lots of observations at a wide range of frequencies, covering a wide range of astronomical species and astrophysical phenomena from the ground. Why does the ground matter so much? The ground matters because you can actually build big telescopes to the ground. So you can have big light buckets collecting a lot of photons, and that lets you have a very, very high sensitivity. So for comparison, if you think about the Hubble Space Telescope, that's a fantastic telescope. It's a wonderful telescope in ultraviolet, optical, and near infrared. But the HST is a tiny telescope. It's 2.4 meters in diameter. If you compare the HST to the biggest optical telescope on the ground today, the biggest telescope is 12 meters in diameter. And remember, the collecting area of a telescope goes with a square. So the HST is about 36 times smaller in area, 30 times smaller in area than the biggest optical telescope. And there's about a dozen telescopes on the ground today, which are about 8 to 12 meters in diameter, much, much, much bigger than the HST. It's very hard to put a big telescope into space. The JWST, the James Webb Space Telescope, which will fly with any luck this month, is going to be 6 meters in size. And that's big, but that's still nowhere in comparison to a 12-meter telescope. And what we're planning to build in the ground in the next decade is 30-meter size telescopes. So that, even the JWST is going to be a factor of 25 smaller in area than these gigantic buckets like the 30-meter telescope, the European Extremely Large Telescope, or the Giant Magellan Telescope. And that tells you why observing the ground is so important. The same thing exactly applies in the radio. You can build these big telescopes on the ground, like the GMRT, the Giant Meter Wave Radio Telescope, the Very Large Array in New Mexico, ALMA in Chile. And as I said, the radio sky goes from about 10 megahertz to about 1 terahertz, spectacularly large frequency range. The optical sky is very narrow in wavelength or in frequency. So the range of phenomena that you capture on the radio is very wide, and you can capture them from the ground. So both of these tell you that you can do a lot of super exciting science in the radio. What's next? The problem with the optical, as any of you would have known if you had looked at the sun when it's setting, is that unfortunately there's lots of dust in the universe. There's dust, of course, in the planet, but there's also dust in galaxies. And dust is a nasty thing because if there's dust on a line of sight, it basically obscures optical and ultraviolet radiation. And the top panel over here, so the right side, the two figures, show you a region of the sky in the Milky Way, which is called, this region is called Barnard 68. It's a dark cloud. And so all of these beautiful things, this is a VLT optical image, and you can see this rich region, full of stars over here, and then this completely black region over here. And so you would say, what on earth is this? This is a hole in the Milky Way, which has no stars. But then if you go and observe this in the near infrared, again with the VLT, you can just about see very faint emission from objects in this region. And these objects are actually really bright stars. All that's happening is that this region is enshrouded by a cloud of dust, by a molecular cloud, which contains a ton of dust. And that dust is basically obscuring light from the background stars. So the only reason that you see these stars is that there's no dust, there's not much dust between us and those stars, while this region has lots of dust. And so optical and ultraviolet observations are severely affected by obscuration by dust. And that really has implications for your estimates of conditions in objects which contain dust. For example, if you estimate the star formation rate of a galaxy in the optical, very often you dramatically underestimate the star formation rate because the emission in the optical is being killed by dust. And the beauty of the radio is that radio observations are not affected by dust at all. So dust is basically transparent in the radio. And just to emphasize this, I thought I'd show you an image of what is called HDF 850.1. So HDF 850.1, HDF stands for the Hubble Deep Field. The Hubble Deep Field was, until recently, the deepest optical image ever made. And you say, okay, this is fantastic. This is the deepest image you could make with the Hubble Space Telescope. But this region of the sky was also observed in the submillimeter. And in the submillimeter, they found this spectacularly bright source. Submillimeter is about 300 gigahertz. They found this spectacularly bright source. And the weird thing was that if you look at the HST optical image, this plus over here marks the location of the submillimeter source. And there's nothing there in the HST image. And so you'd say, what on earth is going on over here? What is this object? This is some extragalactic field. It's some region of the sky where there's no emission of the Milky Way. So what on earth is this object which is so powerful in the submillimeter and not seen at all in the HST spectacularly deep image? And it turns out that this is a gigantic galaxy called a submillimeter galaxy. And what you see over here in this orangish image here is actually an overlay of a C plus 158 micron spectrum, an image in a C plus 150 micron light overlaid on this HST-like image. So this galaxy, for example, this thing over here is this object over here. This bright thing in the black is this object over here, and so on. But the contours that you see over here are the C plus emission from this object HTF 850.1. And so the redshift of this object is actually measured in radio spectroscopy. We could not measure its redshift in the optical just because it's so dusty, and you couldn't even see it in the optical. But it was seen in the radio, and this object has a redshift of 5.1. It's a super high redshift object. So the existence of these objects were actually not known until the late 90s, until 1998, in fact, when the SCUBA instrument on the James Clerk Maxwell telescope was built. And it suddenly found this whole host of what are called submillimeter galaxies today, really bright objects in a submillimeter. And those are bright because the dust bump that you saw a little while ago, that bump that you see in the far infrared, gets redshifted into the submillimeter. And the dust in those galaxies completely obscures their ultraviolet and optical light. So you barely detect them. If you have to go really, really deep to detect them, and for some of them, even after going really deep, you don't detect them in the optical and UV. But you see them really bright in the radio and the submillimeter. So that's an example where the radio really does spectacularly because it can overcome dust extinction. Next, radio interferometry. Interferometry is a way in which you can get resolution. So one of the things that you really desperately want in astronomy is angular resolution. You want to be able to work out the structure of objects. And with radio interferometry, with telescopes like the Very Large Array, the GMRT, the ATCAM Large Millimeter Submillimeter Array, you can actually combine the signals of multiple single dishes and synthesize a single telescope using this and make an image of the sky. And this gives you a much better resolution than that of a single dish telescope. And the reason is that the resolution of a telescope is basically lambda by d, where lambda is the wavelength, approximately, d is the diameter. Now, for a single dish telescope, like a single, let's say a 30-meter dish, d is 30 meters. But now when I do interferometry and I construct a telescope, synthesize a telescope of using a separation of 35 kilometers or 30 kilometers, my effective diameter is 30 kilometers. That's 1,000 times bigger. And my wavelength is the same. So I wind up with 1,000 times better resolution, angular resolution, with an interferometer than I have with a single dish telescope. And that's the game in interferometry. But to do a comparison between the optical and the radio, the best telescope in the world in the optical is the Hubble Space Telescope. It's sitting above the atmosphere. And so a typical wavelength of the Hubble Space Telescope is 6,000 angstrom. And the HST is 2.4 meters in diameter. And that gives you an angular resolution of about 0.05 arc seconds, 50 milli arc seconds, which is pretty damn fantastic. From the ground, you would get 0.5 arc seconds. So it is a factor of 10 better than the ground. And that's great. The Very Large Array in New Mexico has a longest frequency, a highest frequency of 43 gigahertz or 7 millimeters in wavelength, and a longest baseline, a longest separation between antennas of 35 kilometers. So that's got 27 antennas, which are shown over here very close to each other, and they can move on the rail track, and they can move to a maximum separation of 35 kilometers. In this configuration, they are shown in their most compact configuration, where they're all within 1 kilometer, but they can be stretched out to get to a distance of 35 kilometers. And that gives you a resolution of about 0.04 arc seconds, slightly better than the Hubble Space Telescope, but comparable. So you'd say, okay, that's not so spectacular. This is ALMA, the Atacama Large Millimeter Submillimeter Array, which has 50 of these millimeter wave dishes sitting up on the Shashmantor Plateau in the Atacama Desert. This is an absolutely gorgeous site. If you ever go over here, there's this beautiful volcano in the background called Likan Kabur, which is about 5,900 meters in height and has a lovely lake sitting at the top, which you can hike up to. It's quite a place.
Panda's tips and tricks tutorial. And this tutorial is from mine.
Sorry? Okay, that may have been a background again. So ALMA goes to a frequency of about 1 terahertz, 900 gigahertz or so, which is lambda of about 0.3 millimeters. And ALMA has a longest baseline of 16 kilometers, which is gives you a resolution of about 4 milliarc seconds. So now a factor of 10 better than the VLA. And then to get even better than this, you can do, there's a telescope called the Very Long Baseline Array, 10 telescopes distributed over the United States, going all the way from Hawaii to Arecibo, and then 8 telescopes on the continental US. And that has the longest, a shortest wavelength, if you like. That's not really the shortest, it goes up 90 gigahertz, but choosing 7 millimeters, the same as the VLA, the distance is 10,000 kilometers. And you wind up with R of about 0.15 milliarc seconds. And that again tells you that the VLBA has a resolution, which is, as you can see, nearly 300 times better than that of the Hubble Space Telescope. And you probably saw the Event Horizon Telescope images of the black hole in M87. Those are made using very long baseline interferometry at 300 gigahertz. And of course, that's not a spectral line image, that's a continuum image. But the VLBA can be used for spectroscopy to actually, for example, the water masers. That's fantastic. You can actually get crazy resolution in regions around active galactic nuclei. So moving on to the last issue of why you should love radio, the main parts of galaxies are dark matter, stars, and gas. And if you want to understand galaxies, you must understand the baryons, the stars and the gas, and the dark matter, of course. You can look at the stars and the gas, the stars in the interstellar medium. And the point to be really emphasized is that galaxies look very different in stars and gas. And this can be emphasized by looking at an optical image of the very famous galaxy NGC 6946, which has these gorgeous spiral arms over here. That's a lovely optical image. And this shows an image of the same object in atomic hydrogen in the 21 centimeter line, and these are to scale, on the same scale. And you can see that the atomic hydrogen extends about a factor of 2 larger than the spiral arms in this galaxy. And this is a big spiral galaxy. If you take small galaxies, the atomic hydrogen extends even further. The stars are much, much, much more compact. The atomic hydrogen is often 10 times bigger, 8 times bigger than the stars. So to understand galaxies, you must look at the interstellar medium. And the critical spectral lines of the interstellar medium, the 21 centimeter line, the CO rotational line, the C plus line, all lie at radio wavelengths. Another beautiful thing of the radio is that because of interferometry, I can actually make these 3D spectral line images. I can image the region, as I've done over here in NGC 6946. I can make spectral images, spectral cubes essentially, and I can get velocity fields. I can work out the velocity distribution of the gas. And that again is special in the radio. It's now just about becoming feasible in the optical with what are called integral field spectrographs, which are being installed now which have been installed now on the big optical telescopes like Keck and the VLT. But these have been standard practice in the radio for 40 years now. We can actually get velocity fields of galaxies all the way out to high redshifts. So finally, let me give you I think I'm close to out of my time. In fact, I'm out of my time. But I'll just give you a very brief summary of a few good radio lines. First, of course, is the 21 centimeter line of atomic hydrogen. As I said, this is a hyperfine line at 1420 megahertz. And this lets you measure the atomic gas mass of galaxies. It lets you measure galaxy sizes, and which you saw just now, are much, much, much bigger than the sizes measured in stars. It lets you measure rotation curves of galaxies and, for example, probe the existence of other forms of matter. It lets you measure gas temperatures. It lets you measure the magnetic field strength in galaxies, all kinds of stuff. And I'll talk about this in more detail on Monday. Then you have the CO rotational lines. Rotational lines at a frequency of 115.27 multiplied by J, where J is the rotational quantum number. And this lets you measure the molecular gas mass of galaxies. That's a primary science output, although you get a ton of other things as well, but that's the main thing I would say. And so far out to redshift is about 6.5. The C plus 150 micron line is a superb line. It's a fine structure transition ionized carbon. It's at 1.9 terahertz, 901 gigahertz. And this line is special because it's the strongest cooling line in galaxies. It's the line that carries energy away from galaxies. It causes gas to cool. And this line in the Milky Way, just in this very narrow line, it contains 0.5% of the entire galaxy's luminosity. So if you integrate the galaxy's luminosity from the gamma rays all the way to the radio, do the full integral, this one really narrow line contains 0.5% of the full luminosity. And that should tell you how strong the line is. And of course, this is not really a radio line. It's redshifted it's a far infrared line, but it's redshifted into the radio band at high redshifts, and it's easy to see in high redshift galaxies. And that makes it wonderful to detect and to map the kinematics of high redshift galaxies. And this line has resulted in the first detection of disk galaxies at really high redshifts larger than 4 recently. So you can do the kind of stuff, the stuff that we do in the local universe with 21 centimeter, we can do with the C plus line at redshifts of 6, and that's fantastic. H2O megamasers, I didn't really talk about this at all, but these are megamasers at 22 gigahertz, seen in the H2O line, arise from a strange population inversion. I won't go into that. But these arise from disks sitting around active galactic nuclei. And these are super interesting because they actually allow you to measure both the mass of the black hole. This has been done to death, and you get masses about 40 million solar masses. But even more interesting, they let you measure the Hubble constant. They allow you to measure the Hubble constant. And that's been done, and this has resulted in what I would call a crisis, of what has been called a crisis in cosmology right now, where the Hubble constant measurements from the nearby universe are turning out to be slightly higher than the Hubble constant measurements from the microwave background. And so that is pushing, I mean, there could be some systematic effect that people don't understand as yet. But right now, there is evidence at about the 4.5 sigma level that the Hubble constant from the early universe measurements is not the same as the Hubble constant from the local universe measurements, which could be pointing us towards interesting new physics. And finally, there are lines, there's ammonia, there's methanol, there's OH. All of these, because of fairly complicated physical effects, actually allow you to probe redshift evolution in the fundamental constants of physics in quantities such as the fine structure constant, the ratios of the proton-electron mass, the ratio of the proton mass to the electron mass, and so on. And this lets you test for physics beyond the standard model of particle physics and general relativity. And again, it's a fairly active area of research. Somewhat, I would say maybe somewhat of a niche area of research, but certainly an area of much interest. And so this gives you kind of a big picture view of a bunch of fun things that you can do. And of course, this has a strong, cosmological bias, partly because, I am very interested in cosmology. So to summarize then, I hope I've convinced you that astronomical spectral lines probe the physics and chemistry of gas in stars and galaxies, as well as the structure, content, and kinematics of the gas and of the object that you're looking at. And you can use these lines to measure galaxy sizes and dynamical masses. You can use them to measure gas densities, temperatures, and pressures, and again, masses and magnetic fields. So what more do you want? Most importantly, I think spectral lines provide velocity information. And this is super important because this lets you measure the expansion of the universe. And of course, in more recent years, the acceleration of the universe. If you didn't have spectroscopy, you would not be able to infer the presence of dark energy in the universe. It lets you measure the cosmological distance scale and hence the Hubble constant. Lets you measure the velocity fields of galaxies and hence find evidence for dark matter. It lets you probe the origins of life via searches for extremely complicated organic molecules, for example, glycine today. It allows you to find and study the first galaxies, to test cosmological predictions, and to completely jump to study planet formation by using ALMA, for example, to observe gas and protoplanetary disks. It allows tests to standard model of particle physics and cosmological timescales via studies of fundamental constant evolution, and it allows a ton of other things. I've just picked some random things which I'm personally interested in and put them down over here. I could have made probably 10 more slides like this, which will tell you other things that you can do with spectroscopy. So I think I'll end then over here. I apologize for going slightly over time, but yeah, I'll take any questions you might have. Thank you.
So we talked about the effect of Doppler shifting, because of the movement of these objects with respect to us, and how it redshifts and blue shifts object. But how about source something like gravitational redshifting? Does that contribute anything significantly to these spectra?
So you do actually see evidence of it's okay. That's a good question. It is not easy to measure the gravitational redshift with spectroscopy. I should be a little bit careful with that statement. The place where you can actually see the effects of gravitational redshift are in things like in observations of the cosmic microwave background, where you see that the temperature is a little bit colder, is a little bit different in the directions of clusters. And it's not really gravitational, I would call it gravitational redshift. It's actually a loss of energy as the CMB photons are coming out of the gravitational well of the cluster. It's not easy. I mean, the effects of gravitational redshift are not very strong.
Hello, sir.
Yeah.
So you mentioned this scale that is used to measure the redshift, right? Like this is like 5 scale redshift and 5 points redshift. I'm not familiar with this. Can you?
Sorry, what scale? I beg your pardon?
The redshift scale. You use that this object has a redshift of like 0.9 or of 5.
Okay, yeah.
So I'm not that familiar with this like scale. Can you elaborate?
Oh, okay. How shall I do this? Okay. So do you know that the universe is expanding?
Yes, sir.
Are you familiar with that notion? Okay. So what's happening is that the universe is expanding, and it's expanding in a uniform rate in all directions. Now, the result of this expansion is that nearby objects are moving away from us and moving away from all points of the universe with some effective velocity, right? They're moving away from us. More distant objects are moving away from us with a slightly larger effective velocity. Even more distant objects are moving away from us with a slightly larger effective velocity. Thinking in terms of Doppler shifts, there's like a cosmological Doppler shift. All these objects are moving away from us, which means that their spectral lines would be shifted by the Doppler shift towards the redder parts of towards the red, if you like, right? That's just a Doppler shift.
No, I actually get that, but
okay.
This notion of like the scaling of redshift, it's only for the cosmological redshift, not the kinematical one.
No, the kinematical one. So the kinematical one is a velocity. That's why one should be a little bit careful. So you define the redshift. The cosmological redshift is not a velocity. You can think of it as a cosmological Doppler shift, but I would strongly advise that you should not think of it that way. You should think, I mean, it's an expansion of space. It's not really a motion of an individual object relative to us. But because that motion results in the lines, in the spectral lines of that object shifting towards the red, you can define this thing in terms of as a redshift, where you simply define the redshift as 1 plus z is lambda observed equal to 1 plus z multiplied by lambda rest. So that is, if you like, the definition of the redshift. Another way of thinking about it is that all lengths are stretched by the expansion of the universe. So a wavelength is also a length. So the expansion of if I take a ruler and the universe expands, the length of the ruler is being stretched because of the expansion. So a wavelength is also a length, and so the wavelength is also stretched just by the expansion of the universe. So that's a more physical way, I would say, of thinking about it than a cosmological Doppler
So
shift.
I actually understand that. I was just confused about it, that you use some term of like scaling of this redshift. That this so you were referring to cosmological redshift at that time.
Oh, for sure. Yeah.
Because I got confused in the case that that there is some specific measurement you have for each redshift, each kind of redshift.
A specific measurement. I'll have to go back, and I'm not quite sure to what you're referring of here. Could you just point me to the slide at which in which this was said?
You mentioned it twice or thrice that okay, this object has a 0.9 scale redshift, which is like high. This object has 0.5. So
right. So that object has a redshift of 0.9. That's a
right.
cosmological redshift.
All right.
There's no scale involved over there. Okay. Another way of thinking about it is that any redshift which is larger than about 10 to the minus 3 or so, 10 to the minus 2 maybe, is a cosmological redshift. And the way of thinking about this is that think about velocities. A redshift is essentially, you can write a redshift as in terms of a velocity as v equal to c times z, where z is very small. So when the effective velocity becomes of the order of the speed of light, then you should really worry about cosmological effects. So if your redshift is tiny, the motions that you get around galaxies are of the order of 10,000 kilometers per second. Anything much larger than this is a cosmological redshift.
All right, sir. Thank you.
Yeah. So there's no way of getting a redshift of 0.9 from normal astronomical motions.
Hello, sir.
Yeah.
Sir, I had a question about metallicity and paucity of cooling routes, sir.
Okay.
Means how it is affected, means how it is measured by spectroscopy that the redshifted galaxies, they show this type of behavior, sir.
Okay. So let's look at this. Let's look at the spectrum over here. So, for example, over here, you can measure the strength of these of these different metal lines, right?
Yes, sir.
And so you can measure the amount of metals relative to hydrogen. So I can measure the amount of hydrogen with the Lyman alpha absorption line. I can measure the amount of, for example, iron or silicon from these absorption lines, and I can take the ratio of one to the other. So the ratio of the amount of silicon to the amount of hydrogen gives me the metal abundance in that system. And the metallicity is defined as that ratio relative to solar metallicity. So I take the ratio on the sun, and I get the metallicity of that galaxy or of that small sight line, right? Now, what you will see is that if you look at small galaxies, like, for example, dwarf galaxies, these objects have much lower metallicity, a smaller metal abundance for the amount of hydrogen gas that they have than big objects like the Milky Way. What you also see is that if you go to higher redshifts, high redshift galaxies have lower metallicities than low redshift galaxies for the same mass of the galaxy. And the argument is just that you need to produce, so metals are basically formed by stars. And so what happens is that when you have star formation, the stars will go supernovae, and the supernovae the stars will produce metals, and the supernovae will throw these metals into the galaxy, into the interstellar medium. And that increases the metallicity. So the more star formation you have, the more metals you have. But now things get interesting, because it turns out when you have metals in the interstellar medium, those metals, for example, the ionized carbon, the C+ line, or the oxygen 1 line, they can actually carry energy from the interstellar medium out of the galaxy or out of that region. And the carrying of this energy causes the gas to cool. So the cooling of the gas will cause the gas to condense into smaller and smaller regions, and will again result in more star formation. So it's like a cyclical process. You produce, star formation produces supernovae, which produces metals. Metals cause the gas to cool. The gas forms stars. That forms more supernovae and more metals, and so on, until you eat up all the hydrogen in the galaxy. And so you can see that as time goes on, a galaxy's metallicity will keep increasing. A galaxy which doesn't have too much of star formation will have a low metallicity because it hasn't produced too many metals.
Okay, sir. Okay, thank you, sir. Thank you very much.
Yeah.
Sir, so is atmosphere opaque to wavelengths greater than 10 meters?
Yes. So it's actually more like 30 meters. And that happens because the plasma frequency of the atmosphere is about 9 megahertz. And so radiation at frequencies less than 9 megahertz, the frequency is less than the plasma frequency, and hence radiation can't propagate. So we have the ionosphere above us, and that has a plasma frequency.
Okay.
Sir, I had one more question. If it's okay, can I ask you a question about the event horizon spectrum?
Well, there's no spectrum in the Event Horizon telescope. It's
Okay.
a continuum observation. It's a broadband observation.
Okay, sir. Okay.
Yeah.
Fine.
Sir, I have one question. Like you showed the spectrum of from the distant quasars. So
Yeah.
there we had ionized carbon, which was like relatively very strong.
Yeah.
So my question is that why it is so, that what is why the carbon is so much ionized there, and
Okay, that's a
what are
good
the
question.
physics behind it? If you can.
That's a good question. So the amount of ionized carbon compared to neutral carbon and how much the carbon is ionized, you need something to do the ionization. You need some source of energy. The two standard sources of energy in objects are stars and active galactic nuclei and collisions, right? So in the case of over here, that's a quasar. A quasar is a gigantic black hole, which is basically onto which matter is falling, is accreting, and it is giving out a huge amount of radiation and also giving out a huge amount of kinetic energy. There's lots of flow of particles coming out. And it's the combination of this radiation, mostly the radiation, which causes the ionization of the carbon. So if you have, the general rule is that if you have a lot of gas near an active galactic nucleus, there's a large source of energy right there, which causes the most particles, or most the favored state, if you like, is the ionized state. So you will tend to not have too much of neutral carbon near quasars. You will tend to have neutral carbon in cold regions. So for example, the molecular clouds in the Milky Way or nearby or galaxies, you will tend to have carbon in the neutral state. And another way of thinking about it is that the ionization potential of carbon is about 11 electron volts. And so therefore you can, if you simply have energies more than about 11 eV, then you can basically ionize the carbon.
So,
sir, I have a question.
Yeah.
so maybe
sir,
the last one, so that we can round up and prepare for the next session. But maybe that's one, Nassim, yeah.
Yeah, that's fine. Yeah.
Right.
Yeah. Okay. So sorry, unfortunately, I'll have to break over here. So if any of you have any more questions, you can always send me an email to ask, and I'll do my best to reply. My email address is you can just find it from the NCRA webpage. Yeah. Okay. So thanks, and see you.
Thank you very much, sir.
Thank you.
Listen, before we close, we take a gallery shot. So if you stop share screen, shot,